Transition metals operate as the rigorous hubs of microscopic architecture. A transition metal snaps into place at the center of a highly organized geometric frame. We call this core a Lewis acid, an electron-deficient metal cation. It acts as a docking station for ligands, Lewis bases carrying pairs of electrons ready to donate. Together, they establish two distinct boundaries: a rigid inner coordination sphere, where the primary architecture lives, and an outer ionization sphere that loosely holds balancing ions. This breakdown of copper sulfate tetraamine illustrates how we notate these zones. The metal and bonded ligands are tightly grouped inside square brackets. In water, outer sulfate ions break away entirely, but the inner coordination sphere remains locked together as an unbreakable block. A true coordination compound is defined entirely by this rigid, non-dissociable inner architecture. But how does the metal decide when its architecture is finished? What dictates exactly how many ligands it takes to achieve stability? The thermodynamic driving force behind this assembly is mapped out by Sidgwick's effective atomic number, or EAN, rule. The EAN formula calculates total electrons, Z minus oxidation state X, plus ligand electrons Y. For cobalt, Z is 27, minus an oxidation state of 3. 6 ammonia ligands donate 12 electrons. The EAN resolves to 36, matching the stable noble gas krypton. Coordination architecture is driven directly by the metal's thermodynamic desire to replicate the electron configuration of a noble gas. Before analyzing the 3D geometry of these compounds, we have to properly catalog their ingredients using IUPAC nomenclature, a precise linear code. Look at this list of structural syntax rules. To describe the coordination sphere, you list the ligands alphabetically first, followed by the central metal and its oxidation state. The rules also specify that negatively charged ligands get a distinct naming convention, modifying their ending to an O, while the metal itself might end in 8 depending on the overall charge. Combine these conventions and you get highly descriptive, exact strings like sodium pentacyano nitroxyl ferrate. That IUPAC name is the complete inventory for the coordination sphere, establishing exactly what parts we have to work with. Valence Bond Theory, or VBT, is the mechanism explaining how those parts actually connect, detailing how vacant hybrid orbitals on the metal overlap with the ligand's filled orbitals. The strength of the incoming ligand dictates whether the metal's internal d electrons remain separate or are forced to pair up, which locks in the complex's final geometry and magnetic properties. This table comparing two different iron complexes perfectly illustrates the physical difference between weak and strong ligands. In the first complex, water acts as a weak ligand. It lacks the force to make the 3D electrons pair up, leaving 5 unpaired electrons. To make room for the bonds, the metal uses outer 4D orbitals, resulting in an sp3d2 hybridized, high-spin complex. Contrast that with the second complex. Cyanide is a strong ligand. As it approaches, its repulsive force is strong enough to force those 3D electrons to pair up against their natural tendency. This forced pairing clears out space in the inner d orbitals, allowing for a tighter inner-orbital d2sp3 hybridization. Ligand strength is the primary variable that overrides the metal's default state, dictating the entire internal electronic architecture. That internal electronic shift becomes highly visible in complexes with a coordination number of 4, where the metal must adopt one of 2 drastically different 3D shapes. This text explains why the nickel chloride complex forms a tetrahedron. Chloride is a weak field ligand, meaning the nickel's d electrons remain unpaired. Because the inner orbitals are occupied, the metal relies on 1s and 3p orbitals, resulting in sp3 hybridization. To minimize repulsion in 3D space, those 4 sp3 orbitals push away from each other at exactly 109.5 degrees, constructing a 3-dimensional tetrahedron. Swap the weak chloride for strong cyanide ligands, and the outcome completely changes. The strong cyanide forces the nickel's electrons to pair up, freeing an inner d orbital and creating a new dsp2 hybridization. Geometrically, dsp2 orbitals behave differently. They align perfectly flat, at 90-degree angles to each other, creating a strict 2-dimensional square planar geometry. The microscopic strength of a single ligand determines whether a molecule exists as a bulky 3D pyramid or a completely flat tile. That rigid geometry leads directly to stereo-isomerism. This is a state where two molecules have the exact same chemical formula and identical bonds, but entirely different spatial arrangements. Take a look at this diagram of a square planar platinum complex. We have two ammonia ligands and two chloride ligands. If the matching ligands are placed adjacent to each other on the plane, it's the cis isomer. If they are placed across from each other, it's the trans isomer. In larger octahedral complexes, like this cobalt example, the positions are grouped by faces of the octahedron, known as facial or FAC isomers, or along the meridian, known as mer isomers. The rules of geometry get even stricter with optical isomerism, where a complex lacks any internal plane of symmetry. When you mirror an optically active complex, the reflection cannot be perfectly superimposed back onto the original molecule, establishing a distinct right-handed and left-handed version. In coordination chemistry, the physical, spatial coordinates of the atoms dictate the chemical properties as much as the atomic elements themselves. This creates a unified pipeline. The metal seeks stability through EAN math. The incoming ligands force an electronic hybridization via Valence Bond Theory, and that hybridization locks in the macro-level geometry. Put a platinum atom through this pipeline with 4 specific ligands, and the math dictates a flat DSP2 square planar frame. Depending on how those ligands snap into the available slots, you end up with either the cis isomer or the trans isomer. Here is why that spatial arrangement matters in the real world. The cis isomer is cisplatin, one of the most effective anti-cancer drugs ever discovered, while the trans isomer is medically useless. Because its chloride ligands are adjacent, cisplatin has the exact spatial geometry required to bind to a cancer cell's DNA, freezing its replication. Transition metals are highly disciplined architectural hubs. By understanding the rules of orbital hybridization and ligand geometry, we can predict exactly how these molecules will function in three-dimensional space.